75 degrees by in order to convert it to radians?
Pi over 180.
Pi over 180. There are pi radians in 180 degrees, so my units degrees end up canceling out. I get 75 pi over 180. Now, if you leave your answer in that form, am I going to be a happy camper?
No.
No, why not?
Because you want it simplified.
It's got to be reduced. Come on, you know, this isn't pre-algebra class. Obviously, this has at least factors of 5 in it, so we need to simplify that. So we can take at least a 5 out of both. That becomes 15 pi over 36. So that would be the form I would expect it in.
That's perfect.
Thank you.
You don't want it in decimals?
And we need to go further, because what else can we take out?
3.
We need to take a factor of 3 out. So it become 5 pi over 12.
Now, you wouldn't like it in decimal.
I would not like it in decimal.
All right.
I would be grumpy if you put it in decimal. Grumpy is not good when I'm grading your exams. So no, I wouldn't do that. 46 degrees?
46 degrees is pi over 180.
Times pi over 180 again.
That would be 46, so 46 pi.
46 pi over 180.
Factor
And
out.
what are you going to take out of it?
You can factor out at least 2.
That's all we get to factor out, because 23 is prime. So this will be 23 pi over 90. Is it possible to get nasty, horrid little things like that? Well, of course.
Yeah.
Because 46-degree angles exist in the world, and 42-degree angles exist in the world, and all kinds of stuff. How about this one?
41 pi times 180 over pi.
So we're going to multiply this by 180 degrees over 2 pi. Now, conveniently, what cancels?
Pi.
The pi cancels, which is convenient because it's a messy decimal. So we're going to get 2.1 times 180, so that'll be, what, 360 and 18? 378.
Yeah.
So we get 378 divided by, that'll be 378.
Yep.
Period.
That's it.
Got it.
And so why do you,
Wait, what about the 2?
Yeah, I'm looking, that's, no.
Because it shouldn't, no.
Negative divided by 2.
No, because you have 180 over
Oh, it should just be
5.
180 over pi. You say, what's going on? Yeah, it's 180 over pi. Thank you. Not 2 pi. So, good catch. How about this one?
You come out with 2,573.04.
Yeah, this is one of those situations where since this is actually a decimal, you're going to convert this to a decimal. So since this is already a decimal, you're going to already convert this to a decimal. When you multiply it out, I did not have my calculator with me. This is 57 times 14. 800.
Okay, I messed up.
800 and
So
818.
everyone likes pi.
Thank you very much. Since a certain somebody is borrowing my calculator since he left his at home.
It's 8.
Can I move this? Sure. How about if I put it right here in front of Emerson? All right, I'll move it off to the side. So you can do these conversions just fine, right?
Yeah.
Good. Please don't miss them on the test. It's terrible to stumble out of the starting gate. 6.2. 6.2 is when we did linear velocity and angular velocity. And this is only a little bit confusing, thankfully. Only a little bit. Okay, what does linear velocity measure?
How fast something is going.
It measures how fast something is going in a straight line. We would normally think of linear velocity like if a person's running or how fast a car is going. So when you talk about linear velocity, you're saying, okay, the person, the object is moving in a straight line. How fast is it going? How many feet per second or how many meters per second? Okay, what's angular velocity?
How fast it's spinning.
Angular velocity is how fast something is spinning, how quickly the angle is changing. So if you take a look in your books, you see the definitions on page 352 and 353. What Greek letter do we usually use for angular velocity? Not theta. Theta is what we usually use for angles.
Omega.
We use omega. Omega equals theta over t, where omega is angular velocity. Now, you'll remember that I had two balls that I used to try to illustrate this. Let's say I have two balls and they're covering the same amount of distance in the same amount of time. So I'm standing here and I'm rolling the balls over to that side of the room. And I have one ball that has a radius like this and one ball that has a radius like this, but they're doing the same distance in the same amount of time. Which one has the faster angular velocity?
Small ball.
The small one, because that little guy is going, he's whipping around really fast to cover the same distance. The big one's just going and rolling slowly while the little guy's going. They have the same linear velocity, but their angular velocity is different because this one is rotating, making complete rotations faster. Yes? So how fast you're making a complete rotation is angular velocity. How much distance you're covering in a straight line is linear velocity. Yes? So if this is the form for angular velocity, now when we were in third and fourth grade, we had a formula that we used to have, and you probably did too. We used to say rate times time equals distance. Now we don't use the word rate anymore. We use the word velocity now that we're grown up. What happens if I divide d by t? What do I get?
Velocity.
Yeah, this is analogous to the angular velocity formula. This is how many radians I'm turning in the amount of time. That gives us angular velocity. Yes? Now take a look at the second definition. It's the bottom of the next page. It's linear velocity. What's the formula for linear velocity? I'm actually in section 7.2 at this point. I know some of you are still in the review section. But take a look at section 6.2, 353, page 353. What's linear velocity?
V equals r theta over t.
V equals r theta over t. Okay, now look at this and look at this. What's the difference?
R.
The difference is r. Well, if I look at r theta taken together, what was r theta in section 1?
Area.
No,
Or
Radius.
it's this length here.
arc angle.
Remember this, the area of that was 1/2 r squared theta. This arc length here was r theta. So if I take that arc length and divide it by time, we get another form again of velocity equals distance divided by time. If the ball is rolling on the ground and I want to know how far it went, I'm asking, well, what's the circumference of the circle? How many times did it roll? This gives me the arc length of the circle that's actually been traversed. So the only difference between angular velocity and linear velocity is the radius of the circle. Now that makes sense because go back and think about the ball example we had. What affects, if I tell you that I have a little ball and I have a big ball, I tell you that the little ball makes 1 revolution per second, and I tell you that the big ball makes 1 revolution per second, which one goes further?
The big ball.
The big ball, why?
Because it has a bigger...
It has a bigger arc length all the way around the ball. It has a bigger circumference, right? So basically, when you're talking about like the circumference of the ball or the arc length divided by time, that'll give you the velocity. Now, folks find some of these kinds of problems confusing. I would suggest that you simply memorize these formulas and remember that the difference between angular velocity and linear velocity is just the radius of your circle in question. Because it makes the problem a lot easier if you've got these two formulas in your head. If you don't understand these formulas or don't understand the relationship of them to one another, it makes the problems a lot harder. So let's take a look at, let's go back to, let me flip back to the study section. So if we're on page 414, lesson 6.2. Determine each angular displacement in radians, round to the nearest tenth. So the first one is 5 revolutions. Now, one of the things that the book does is it's going to give you questions in terms of revolutions. Now, revolutions and radians are not the same thing. If I make 1 revolution, how many radians is that?
2 pi.
It's 2 pi. And so if they ask you about revolutions, you need to be sure to multiply by 2 pi, right? So the first problem they ask us is, if you have 5 revolutions, what is the angular displacement? In other words, how many radians do you turn through? So 5 revolutions equals what?
10 pi.
Okay, that's going to equal 10 pi radians. Now you can do unit analysis on this. If you have trouble remembering how to convert this stuff, 1 revolution is how many radians? 2 pi radians. So depending on the problem, you'll either be multiplying by 2 pi radians per 1 revolution, or you'll be multiplying by 1 revolution over 2 pi radians. This is more typical because usually they'll give you revolutions. Like in this case, if we have 5 revolutions, if I do unit analysis on this, I'm going to cancel out my revolutions. So I get 5 times 2 pi, and that gives me the number of radians. That's my angular displacement. So far, so good?
Yep.
Let's do problem 23, 50.4 revolutions. What is that? Now, if it asks you for angular displacement, the trick there is they're asking you for radians. So if on the test you see, what is the angular displacement, they want to know the answer in radians. So if you're given 50.4 revolutions, how many radians is that?
100.8.
What's that? 100.8 pi, and in this case, go ahead and multiply the 3 point, yeah, and I would accept that as a perfectly legitimate answer. You can go ahead and multiply the 3.14 in there.
316.
Yeah, it should be, yeah, the book says 316.7. Now, let's take the next step and let's talk about angular velocity. What if I asked you, we're going to have 1.8 revolutions in 5 seconds. If I said, what is my angular velocity if I have 1.8 revolutions in 5 seconds? Now, what's the problem with saying 1.8 revolutions?
You got a decimal.
Decimals are normal in life. So no, the problem is not the decimal. What units is angular velocity in?
Well, the other problem is we don't know what time period you're looking for.
5 seconds.
Oh, okay, then you just have 2 pi times 1.8, so you have 3.6.
That's right. He's saying it's 1.8 times 2 pi. Now, let's look at what's happening. What are the units of angular velocity? This is theta in. Theta is measured in radians. This is in radians per second or radians per minute, whatever the time unit is.